Hello, welcome to Calculus. This first lecture we'll be looking at properties of functions and some of the different ways that we can define a function. The definition of a function is an abstraction. We are going to look at the different abstractions so that the meanings that we get for a function can be flexible, but we want to look at the properties that are unique to all of these definitions, and that uniqueness helps us create this mathematical abstraction that we're going to use. Calculus relies on functional thought and functional formats, so we spend a considerable amount of time in the beginning here making sure that we can get as much meaning from functions as we will continue to use them throughout the course. So I'm going to switch over to a Blackboard view here. If I need to point at the Blackboard, I will grace you with my image and point to things at the Blackboard. But for now, we'll see a Blackboard representation of things. So what we want to start with is a definition for a function. So we'll say a function. Oops, let me get that here. A function called f. Right, and this name can change. We can have a function called g. We can have a function called h. But it'll have some name. It's usually slightly scripted to delineate it from other variables. Is a mapping for each element in a set D to one element in a set R. Now, mathematics is a game of sets, and the function ends up being the rule. So we have a couple different ways to describe this type of mapping. The first form that we generally see is that we will look at the mapping as we'll talk about the set. And so this is D, and it contains elements. And in general, we'll work with the set of real numbers or the set of complex numbers, but each number is contained within the domain. Then in the function itself is some rule that goes to elements in some set called R. So we can visualize the function as being those rules. So, and when we say mapping, x2 comes over here and maps to y1. And so the function is the rule that if I drop in x2, I get y1. And maybe x3 also goes to y1. And x1 comes over here to y2. And this one comes off to y3. Each one of these follows a rule. And so this is a set version of a function. x2 only has one corresponding value in R. But that corresponding value, y1, might have come through a couple different things. So we notice that in a function, it's a 1. Each element in the domain maps to only one element in the range. The range itself does not share that reverse connection. And this will be something that comes out. When we go forward, moving from an element in the domain to an element in the range, there will only be one answer. But if we have to go backwards, sometimes there can be two answers. And I'll show you an example because we can think about the next way that we talk about a function. And so since these sets don't necessarily have to be all real numbers or all complex numbers, but we tend to work on all real numbers and all complex numbers, we're going to take this same idea and we're going to turn it into a graph. So let's see here. Let me put a set of axes up. And so we'll say x here and y here. Now, our variables don't have to be x and y. These are just the common variables that we use. And what I can do for my function now, let's see, my function was green, so I'll do green, is I can draw every point. And it's a pair of points. This point here is 1, 1. This point here is negative 1, 1 for this particular function. And what happens is this relationship of one x value to one y value generally gets called the horizontal line test, that any x value only touches the graph in one place. And so vertical line test. I said horizontal, but such is life. So a vertical line from the x value in the domain extended upwards will touch the graph in one point. That graph in one point is the y value. So this is a visual representation of the rule. And in this case, the function I was talking about, let me see, my functions were green, so let me get a green here, was f of x equals x squared. And so whatever x value I put in, I get a y value that follows this rule. Right? So f of negative 1, well, I put negative 1 squared, and a negative squared is 1. F positive 1 squared is 1. And this also illustrates that in the range, the value 1 maps back to two x values that it came from in the domain. So this vertical line test, there's a forward direction to a function. Function takes a domain and maps it to the range. There's not always a one-directional mapping backwards. And so a graph in its own right is a good way of talking about a function. We will come to graphs because graphs have behaviors. Visually, we look at a graph and we can talk about what a function is doing. If I'm here at 0 and I increase my values of x's, I can see in the graph the values of y's are decreasing. So I now have behavior of the function. I can talk about how the values change, not just how to calculate them, but have a description of how they change. And if we can say the essence of anything in calculus, it is being able to talk about how things change, not just the values that come out. And another way that we can look at functions is what's called the black box. I don't know, I always they reminded me of meat grinders. But your domain is here, you plop in an x value, the function does something with it, and it spits out a y value into the range. And so it is a box for computing, and the rules that the function do determine how things move through a function. Now, functions can have different domains and ranges. We naturally start with the idea that the domain is going to be all real values. And this is going to be the natural domain that we work with. So if I write this in notation, so I can say x is in the set of all real numbers. That's a good notation that we can use to talk about this. And so I have a rule, I grab an x value, and it is a member of all real numbers. Or we can write an interval notation that says that my domain, the interval, is from negative infinity to positive infinity. And note, open brackets, because you can never get to infinity, they are always an open bracket. And the nature of a bracket is important here. We can have a different type of domain. I could say that x exists in the set of all real numbers such that x is greater than or equal to 0. So here I'm saying x is in the set of all real numbers such that x is greater than 0. In interval notation, that's a square bracket to infinity. And I have a square bracket here because 0 exists in it. And these boundaries will be very important to what we're doing in the calculus. Whoops, let me get that back down here. Got too big here. There we go. The boundary between numbers and the boundaries are something that we're going to be, as we talk about how numbers change, we have to talk about how we approach the numbers. So our interval notation is important. So let's look at some functions and how their domains and ranges work together. So for example, I showed the function f of x equals x squared. I can give that the domain. So I'll say D is the domain from, and we'll give it all real numbers from negative infinity to positive infinity. Well, when I graphed x squared, I noticed that, well, if I take a negative times a negative, I get a positive. So this thing never returns a negative number. And its range ends up being, I can have 0 to positive infinity. So this rule maps from all positive and negative numbers to only positive numbers and 0. And that's kind of the power of the function and its mapping. Let's look at another function here. We'll have f of x equals 1 over x. Well, in determining the domain for this, we have a problem that we can't divide by 0. So my domain has to go from negative infinity all the way up to, but not including 0. So I put a open parenthesis or open bracket. I think I'll say this is closed and this is open as boundaries, because closed means it contains it, and open means you never get to infinity. And in this case, we never get to 0. We get arbitrarily close to 0. And I'm going to union it with, well, I have to start on the other side of 0. And one of the things what we'll do in calculus is we will look at how close we can get to a number. So in this case, I can get really, really close to 0. I can do 1 divided by 0. And so on. I can get arbitrarily small. So I can get close to 0, just never at 0 itself. And that's something we're going to have to explore in calculus, is how close we can get to these boundaries and what it means. Well, if I put all of these numbers into here, I'm never going to get a 0 out of it, but I will get positive and negative numbers. And so this range is also the same. So there are different domains and ranges for each functions. The general restrictions we have in domains come from the two things. Since we're mapping from real numbers back to real numbers right now, we end up with two rules that really drive any restrictions we have on our domain. So our domain restrictions are we exclude values that cause division by 0, because dividing by 0 is undefined mathematically, and we exclude values that cause even roots of negative numbers. Alright, so you can't have negative 2. So if I have some function f of x is equal to x, then I can't have negative numbers, so the domain has to be from 0 to infinity, because in real numbers, we don't have an idea of what negative 2 is. And we will look at some complex numbers throughout this course, but we will mainly focus on real numbers. So our functions have to have domains that restrict them to having values that don't cause these errors in these errors in the what operations can do. So this is the end of the first video here. I'm going to do some examples of finding domains. As side videos, you don't have to watch those as you go through this. And the next lecture itself, I'm going to look at in a little more detail of graphs.